Start. Are we good to go with the stream? Okay. So what I want to talk about now is getting gas into halos and also see what comes out of them. But it's useful before I get to that to perhaps talk about some of the problems that we face for galaxies. So I talked about this a lot on Tuesday, that we have a stellar mass function, and yesterday we derived the mass function for dark matter halos, the Press-Schechter mass function, plotted in green here, and it had a different shape at the two extremes. So that hints as a problem. It's not so easy to say there's one galaxy per dark matter halo. Okay, that seems easy, but it's not going to work here. That is not the only problem that we face in galaxy formation. Another one is called the missing satellites problem. And this is a simulation. From the name you can guess it was a simulation to try to make a galaxy that looks like the Milky Way. And this image is of the dark matter halo. Now if you take an image of the Milky Way, okay, well, first thing, if you look in the sky, you see two satellites of the Milky Way. It's the Magellanic, small and large Magellanic clouds. Then if you take a deep image, you will see another 20, 30. But not very many more than that. And here, this prediction is that there's going to be a ridiculous number of these, thousands and thousands of these satellites. So why are they not there? Why are they missing? That's the missing satellites problem. And when it was first pushed out, people were perhaps very excited about it. I think it is not so bad anymore, but it's still a problem. And it's difficult, for instance, around the Milky Way, because you sit inside the Milky Way, it's difficult to see everything. So what people have done instead is they've looked at the Andromeda galaxy. And so this is Andromeda, but a bit different from what you've seen before. This is M31. Here is the Triangulum galaxy, M33. And what this is a map of stars. So what they did was they went out and they found stars in the sky and they counted stars. So this is not a picture of the galaxy, it's just a count of stars. The color here determines how many stars there are. So there's no background, there's only stars that live in Andromeda. And what they found was they found all these small satellites. Right, Andromeda 1, 2, 3, 4, they don't have any fancy name, they're just numbers. But if I go back and forth, there's a lot fewer satellites here than there is here. So how do you explain that? That's one problem. And the simplest way to explain that is what I've written here. You just say, okay, when a dark matter halo is sufficiently small, there will be no stars in it. Okay? Maybe it's so small, say it's so small that the only mass of, you can only have 100 solar masses of gas inside it. 100 solar masses of stars might not be enough even to form a single star. Maybe it is enough, but depends on the distribution. So if that's the case, then here you could basically say all the small dots disappear because they are there in the halo of our galaxy, but there are no stars inside them, so you can't see them. A lot of people like that. So that's the simplest way, and then you just get rid of them. You get rid of all the small ones, and you say, okay, the other ones, well, maybe there was a bit of stars formed in them, but when you have one supernova, it's big enough to blow all the gas out. So you might have formed a star, but then you blew the galaxy apart. Okay? One supernova has an energy in the explosion energy of about 10 to 51 ergs. And that's enough to, that's much more than the binding energy of some of these small halos. So maybe they're just blown apart. So that's the idea, at least. And it's thought that this is then called feedback. Okay? So as I said on Tuesday, feedback, we know stars do this. Supernovae do this. But it cannot be stars, as I said yesterday, because it has to be an effect. In that case, it would have to be an effect that got bigger and bigger as you went to small masses, and bigger as you went to large masses and was small in the middle. And there's just no way of doing that. You have to have, this is really two different processes. Something that becomes more and more important in small galaxies and something that becomes more and more important in large galaxies. It has to be something like that. There can of course be many different effects, but that's possible. But there has to be different effects on this side and that side. So on the massive end, what we think is happening is that there is a dark matter halo. And we think this is partially what I talked about earlier, that things take a long time to cool down, means that it's hard to form stars. Because they get into the halo, they're hot, and then they need to cool down to get cold enough to form stars. And to be cold enough to form stars, they need to be about 20 Kelvin. That's a long way from 100,000 Kelvin. So you need to go all the way from 100,000 to 20. That takes a long time, and that's partially why it's inefficient. Now this is the picture I showed on Tuesday, and I like this because of the way the data here are quite reliable. I think this shows an honest picture of things. But people have done this in a more model-dependent way, and this is now turned upside down. So this is actually efficiency. It's the number of stars formed per halo mass as a function of the halo mass. And you can see there are lots of different determinations, most of which use almost exactly the same technique. So the fact that, and the same data, so the fact that they all sort of agree is not completely surprising. But at least they all agree that there's a peak efficiency in halos of about 10 to the 12 solar masses. Those are the halos where gas has been turned into stars most efficiently. And we think that is, if you go back to what I talked about before the break, in this mass, the temperature will be very high, so cooling times are very long, and so the gas that's there cannot easily cool into stars. What does it look like if you go back in time? Well, people have tried to do that. This is much harder. This is the best guess today. Here is the halo mass. The different colors go from black through red, orange, yellow, green, up in redshift. So you can see they're all pretty much the same. I would say everything up to, say, redshift 4, they are identical within the error bars. There's a little bit of scatter, but there's not much of a difference. And they all say that halo masses of around 10 to the 12 solar masses at that redshift is the most efficient at forming stars. And then at higher redshift, it drops down a bit, but the data are less good. But remember, 10 to the 12 solar masses at that redshift does not mean 10 to the 12 solar masses today, because a halo will get more mass. It will accrete surrounding halos, and galaxies will come inside. So this is what the picture is at that redshift. And it tells us that this mass range somehow is the best to form stars in. Like the halo is about that mass. That's when star formation is really efficient. And part of that, I'm sure, is due to cooling. It's very efficient cooling in that kind of mass halos. If instead you plot the same plot, same data, but now you estimate what's the mass of that halo today, okay? Exactly the same data, but here is the halo mass at the time of measurement, and here is the halo mass today. And these halos, you see these ones from high redshift, they have grown a lot. So they're moving this way. And if you go back to this plot, those halos today are very inefficient at forming stars. But back in their time, when they were 100 times smaller, they formed stars very efficiently. And so you see the peak efficiency, so the peak of these curves is very similar. So stars were actually formed into halos at pretty much the same efficiency, but then the halos grew and they became bigger and they stopped forming stars. So it's not like you grow the dark matter halo, you don't grow the galaxy. Okay, you grow the dark matter halo, but because it gets hotter and hotter, it gets harder and harder and harder to form more galaxy. So that's why you kind of reach the maximum size of the galaxy, even though the galaxy is merged from smaller pieces. Okay? So this is similar to this cooling plot I showed before the break, but now we've broken it down into merging systems. So there are some assumptions that go into calculation curves like this. So, you know, how they're not completely wrong, but how reliable they are, I'm not going to tell you. Okay, so let's think about feedback, because that's the story right now. So what happens in feedback? Well, useful to just consider the units of the amount of energy. So the kinetic energy in a supernova explosion, is pretty constant for most supernovae. There are a few strange ones, but most supernovae are very constant, and it's around 10 to the 51 erg. Now, by the time you form one supernova, okay, the interesting thing is how much mass have you formed? And so to do that, you need to know the distribution of mass of stars. So if you assume that the mass of stars is distributed as a power law, and so the easiest is to use saltpeter. So saltpeter. He says that the number of stars is proportional to the mass to the minus 2.35. It's a distribution function. So if you now calculate how much mass, then you say, okay, to get a supernova, I need to have a star that's more massive than 10 solar masses. Okay, it's 8 or 10 depending on the detailed models. Okay, say 10 solar masses. And then you ask how many stars or how much stellar mass do I need to create before I get one 10 solar mass star? And it turns out that you get one supernova per 100 solar masses in total of formation. So since this is telling you that most stars are low mass, you will have a lot of low mass stars before you get one supernova. Okay, and the unit is about 100. So that means that per solar mass that I formed, I get 10 to the 49 ergs, because I need 100 solar masses to get one supernova. So per mass I form, I get 10 to 49. That's very similar to the binding energy of at least the molecular clouds that we have in the Milky Way. So if you calculate what's the binding energy, gravitational binding energy, assuming it's a uniform sphere or something like that, it's about 10 to the 49. So then you can compare this for the binding energy of a galaxy. You can write that down. Take the supernova energy divided by the binding energy, and you get an expression of this kind. Okay? It depends on the circular velocity of the galaxy. So just to remind you, circular velocity is defined more or less like this, and depends a little bit on the distribution of mass, but this is the circular velocity. So I use circular velocity instead of total mass here. That's the amount of stars that I get out of the gas, so the efficiency of star formation. And you can see that in principle, the supernovae give you something like 10 times the binding energy of a galaxy. Okay? You form a galaxy of 10 to the 9 solar masses, and that will give you supernova energy that's about 10 times the binding energy of that galaxy. Okay, it varies a bit depending on the exact size of the galaxy. If the galaxy becomes smaller and smaller, this becomes more and more important. So this goes up, and yeah, exactly. So so when this becomes very small, this ratio becomes large, and the supernova become more and more important. And that fits with the picture we saw before. Okay, so we saw before that we want something that becomes more and more important as you go to low mass, and that's exactly what this picture is telling you. Okay, you go to low mass, it becomes more and more efficient at blowing apart the galaxy. So this is a likely way of blowing apart the galaxy. You put in supernovae. And this is, as I showed you on Tuesday, this is actually something that we see in small dwarf galaxies. There are significant winds that blow gas out of the galaxy. Whether it's enough to really pull apart the galaxy, well, that depends very much. I mean, in this case, not. In this galaxy is not enough supernovae to blow the galaxy apart. Now you can do the same thing for the AGNs. So again, you write down the binding energy. In this case, I wrote down the binding energy of a halo. Okay, this depends on the structure of the mass, virial radius, the mass of the halo, and the mass of the gas. So that's the binding energy of the gas in the halo. Okay. And the energy that comes out of the AGN, that's something that we don't know. We know very little about how AGNs couple to the gas in the galaxy. But we know how the energy of the AGN, what amount of radiative energy it produces, and that's of the order of the mass of the black hole, c squared, and with an efficiency factor which is of the order of 10%. So then you can just divide these two, and you need to have some estimate on black hole mass, and that's the tricky bit here. So it's a bit, this is, the ratio here typically is quite large, so there's a lot of AGN energy, but it depends on this amount of bulge mass, how much central mass there is in the galaxy. Effectively, this is the black hole, and it depends on the efficiency of the AGN. And it's probably fair to say that we don't really understand this. We think something like this happens, but to build a believable, testable physical model of this, it's very hard, and it's not really done. So this should really work on this end, and not at low. At low mass, this probably doesn't work very efficiently because low mass galaxies don't have a bulge, and so they have very low mass black holes. So it's quite a dramatic thing. So the central AGN, relative to the galaxy they live in, if you just take the ratio of the sizes, is equal to the ratio of the sizes of a coin to the size of the Earth. Okay? So the black hole really is a tiny, tiny bit of the galaxy. Really is. And this then, this coin is what's going to govern the Earth. Now, you could of course say that money is indeed what's governing the Earth, but that's a political statement and not a physical one. So in this case, it's just a very large difference in sizes. And that large difference makes it very difficult to understand how these things couple. It's very difficult to make a simulation that really can bridge all that large range in size. So the question then becomes, do you see this? Is this real? And I think there are quite a lot of suggestive results that suggest that this is working. This AGN feedback is working. But I think it's still not fully proven. Here, for instance, is a study from a few years ago. I probably should update this now, where they looked at molecular gas. So that's dense gas in the center of the galaxies. And they looked at these ones being blown out as winds. And what this is plotting is the gas mass divided by the amount of gas that's being lost. So when this is a small number here, there's a lot of gas being lost. This is the time, effectively this is the time in years that it will take to blow out all the molecular gas. And you can see the times are quite short, 10 to the 6, 10 to the 9 years here. And so what they were finding was that the function of the brightness of the AGN, this became shorter and shorter. So that's the idea, is that there's more and more power in the AGN, and it's more and more efficient at blowing away the gas. Okay, the problem with this kind of results is that they are subject to quite a few uncertainties, but it's suggestive at least that stronger AGNs can be better at getting rid of gas than less strong AGNs. And this is, the way they measured this is by looking at these emission lines and find this very broad distribution here in this molecular gas. Yeah?
I've heard about the M-sigma relation, which relates the size of the black hole and the
Yeah.
bulge.
It's only observational, yeah. So you can derive, so simulations will give you an M sigma relation, but they give you an M sigma relation usually because they assume there is a relation, there is a feedback relation between AGNs, and so then it's the same material that's creating the galaxy that's feeding the black hole, and the black hole grows. And as long as those two things are linked together, you'll get an M sigma relation. The problem is at some point you need to get gas in from outside into the black hole, and when the galaxy becomes very big, that becomes harder and harder after a while. So exactly when this happens and when it's established, I think is a bit unclear. But that's what I used in the previous slide. Another place where we see it, we see these bubbles in clusters. That's what I showed on Tuesday. This is high density regions. And you can see there are some hint that these are actually bubbles or shells or something like that. And we think those are just pressure bubbles, high pressures that are blown out from the central AGNs. And there are some models for how that works, and they might be right. So that's the basic story, which I've repeated many, many times now. Star formation feedback, AGN feedback in this part. So so now I think it might be useful to have a quick peek at what simulations show us. Okay, so here is a very old simulation of feedback. What this is doing is a simulation which there's a galaxy forming here, I think it's this way, and it blows out gas in loops, but in this case it mostly falls back onto the galaxy again. It doesn't blow the galaxy apart. And you see the lines here are velocity vectors. So it shows the direction things are moving. And so you can see they go out, go in a loop, and will come back again. In this case, it shows only the cold gas, so stuff that's not being blown out, but just the cold gas in a disk. And there we come. There comes the hotter gas again. And you can see there are these loops that come around here. And these are basically gas being blown out, but there's not enough energy to get rid of the gas. It goes up, it gets hot, 10 to the 5, 10 to the 6, and then eventually it falls down again. And if it's cool enough, then it will form stars again. If it's too hot, it will not form stars again, or at least not for another Hubble time. So this is only stars. Okay, so that very often, this we see observationally. We see these sort of fountains, galactic fountains, or at least we can convince ourselves that we see them. Now, if you go one step further and you start adding AGNs, things look a bit different. So now you're going to see the same movie, first using the gas, and the color here is related to the temperature of the gas, and thereby the density. Now, sorry, this is density, I think. Yeah. And you can see there are these events that might have to do with a black hole that sometimes blow gas out. Okay, we saw one earlier. Should be another one quite soon. Oh yeah, can you see this very faint structure? Well, if not, maybe we could turn off the light. But anyway, the more dramatic is quite obvious. And you can see it's forming here. It's now accreting a lot of gas because it's falling in, and then it blows it out again from the AGN scenario. So this is a picture of doing it. Now you'll see the same thing, exactly the same thing, but now just following the stars. And now you'll see it's a lot more boring. Okay? Of course, there are going to be these beautiful arms, tidal arms, but it's not going to be blown apart. Okay? The stars themselves are mostly going to stay around. You need more energy than this to blow the stars apart. And I don't remember what the coloring is in this particular figure. So, sorry. I think it has to do with what kind of stars are there, but I'm not sure. But you see, in the previous figure, now the gas was just being blown apart. But you'll see one comparison where you see both at the same time. But basically, this one ends up looking very much like an elliptical galaxy. Elliptical galaxies look relatively similar. So this is face on, edge on. Stars, gas. And now you can try to follow it and see the differences. And broadly, they will be similar, of course, because it is gravity after all. Gravity doesn't care about whether it's gas or stars. But when feedback starts, and it already started a bit down here, you can see the gas is much more affected by it than the stars. And the other thing you'll see is that gas is often more concentrated than stars are. And now you can see there's quite a big difference between the gas and the stars. And that's because the gas has now in large part been heated up. You heat up gas, it expands, right? Just standard ideal gas behavior. And in the end, you're left with some chaotic distribution of gas in it, and the stars are well behaved. Now you can put in something that's even more dramatic. Similar story, but not quite the same. You know, two big spiral galaxies. They'll hit together. There will be an increase in density and temperature through a shock. And when these ones come back, they really feed their black holes. Now we're going to see them starting quite soon. They form this bar structure in the center, and that's very good at channeling gas into the center. And now they start heating up and blowing gas apart. So now you can see these winds really being blown out. Each episode of black hole accretion here really blows the gas out. You see, this really gets rid of the gas, right? It's really efficient at it. It just imparts a lot of kinetic energy on the gas, and the gas just moves out. And in the end, you're left with something which doesn't have a lot of gas left at all. And that works very well because elliptical galaxies, if you go and look at an elliptical galaxy, you find it has a bit of gas, but it's very hot. So 10 to the 5, 10 to the 6, 10 to the 7 Kelvin. So this might very well be what the gas in an elliptical galaxy looks like, because the stars in this galaxy actually looks like an elliptical. I don't have it here. So this is at least a pretty picture version of what feedback does. These movies, they're quite old actually, but I used them because this was really the paper that convinced people that this process might be real. Not because the pictures look so good, but because they sort of went through the exercise of, you know, seeing what's really the result of this process. So is this then the solution for this missing satellites problem that I talked about earlier? So this is Via Láctea again. And so in principle then, you could just get rid of them. You say, okay, I'll just put stars in some of them, and then I'll let the exploding supernova rip apart the galaxies. But you need to then reproduce two things. The first thing you need to do is to reproduce the number of galaxies of a particular size, number distribution. Oops, no, I don't want to see that again. And that's what people have done here. So this is this number of dwarf galaxies brighter than some limit, but this is the absolute magnitude of the galaxy. See, these are quite faint. These are, you know, a really bright star in the Milky Way is brighter than this, than a single galaxy here. The Milky Way is in black, and the gray is for M31, Andromeda. And these various dotted curves here are models that that deals with feedback, and they can reproduce this number distribution. This is from a paper by Boyle and Colchin. So they get the numbers right, but do they get the shape of the galaxies right? Well, not so much, because here they plotted here the velocity of this galaxy, and the simulations are all the colored points, and the observations are these points. And well, let me double check that that's actually true. Is that really true? Yes. Yeah. Okay, that was right. And so even though the models and the data worked in numbers, it doesn't work here. Okay, so that's a problem. Maybe we can get rid of that, because this used only dark matter. So one way you can do it is that you can change the shape of dark matter a bit, and that will also change this velocity they measure here. And is there evidence that that's different? Well, there is. So yesterday I talked about the Navarro-Frank-White profile, the NFW profile. It's plotted here as in these gray lines here. There's a bunch of halos from a simulation. As a function of radius, it's a density. Okay, that's simulations, and these are data. So you can see the data actually work really well in this region, but they're flatter in the center than what the dark matter simulations say. Okay, they're less dense. So that actually would help in the previous plot. And so what's the problem? What's happening here? So some people, when they saw this, they thought this is a problem of cold dark matter, because the reason why cold dark matter models have this peak here is because dark matter doesn't have velocity, so they end up a lot of dark matter in the center. They can't move anywhere. What we think is happening here, though, is that when you just make a simulation only using dark matter, you're missing an important part of the picture. You're missing baryons. And so if you put baryons into there, and you release supernova explosions, so have some supernova explosions in the center of a halo like this, what you can do is you can add energy to the center, and you blow it, you puff it up. It doesn't, it basically, you have to blow it bigger, make it bigger, blow it up with the supernovae, and then you can get it flatter. And there's a couple of other effects also, which is the fact that the baryons will fall in and they will slosh around, and they can then affect the shape in the center, but it's mostly to do with feedback. And the way people do this is they observe a profile that looks like this. They start with a dark matter profile that looks like this, and you need to explain this one difference. Okay, the rest kind of works. So what do you do? Well, to calculate that, and I'm not going to do that now, to calculate it, you just take the potential energy, you calculate the potential energy of this, and you calculate the potential energy of this for the same total mass, of course. And then you see what's the difference in potential energy that you need. And that needs to come from somewhere. Okay, so you just, it's very simple. You just say, okay, this is the potential energy. This one typically requires more energy to make this core. You need to add the energy to this one. And this will give you how much. So then you think, okay, that's good. I'm done. I'm sorted. I can do that. That's not very difficult. I know the distribution functions. I can calculate this. But it is a bit difficult. And the reason for it is, if I want to blow these things off, I need this energy. So I need supernovae. I need stars. But if I go back here, I don't need stars. I want to get rid of stars to get rid of these dwarfs. So I have a tension. I need to have the stars to blow up the centers of the galaxies, but I don't want stars because I want to get rid of these. So people have looked at this. So Jorge Penarrubia has, it's probably one of these that have looked more carefully at this. And he calculated the amount of energy that you need to make these cores as a function of the mass of the halo that these galaxies lie in. And he tried to compare this to what you needed in order to get rid of, these missing satellites. And so in order to get rid of the missing satellites, you really don't want to be above these green or blue lines. But in order to create the cores, you don't want to be below these red lines. You don't want to be here. So here, in these very, very small galaxies, there is a real tension. it's difficult to reconcile the missing satellite problem and these cores in the centers. So you might then ask, what's their suggestion? So Jorge has worked quite a lot on warm dark matter. So his preferred possible solution is that he says that this is an indication that this difference here is not only because of baryons, but it is because this is a signature that dark matter has some velocity. Okay? He might be wrong, but you know, it's a cute idea. It's not his idea, it's been around for a long time. But basically, if you had a little bit of velocity, you don't get this cusp in the center and you get a bit of core. So the idea was that this tension here can be relieved by adding some velocity to dark matter. It's of course always true that if you add more free parameters to a model, it's easier to fit them observations. So, you know, this is not a perfect solution, but it's suggestive. Okay. I think it needs more careful work than, I mean, right now this is based on relatively little data. It is based on a fairly simple argument, and it might not be that the argument that he is using, you know, it could be that there are other things that are happening here that wasn't taken into account in the analysis, which is, the analysis they did was essentially what I described. They just calculate this potential energy, the difference, plot it up here, and find out what's the maximum number of stars that you can form and still be consistent with the missing satellite problem. Maybe you need to do a better, you know, more in-depth study, but it's quite interesting. Okay, so now finally getting gas into halos. And the reason why I want to get to this is I want to explain. Oh yeah, sorry.
Before you start with this, when you see the radial velocities of the stars in the galaxy, you see that dark matter dominates after the sun. Does dark matter dominate in all of the graph or just after the sun?
So well, so that's a complicated question actually. So we on the faint end of the galaxy luminosity function, we actually define galaxies to be systems that are dominated by dark matter. Because you can have galaxies and globular clusters that are the same mass, but in terms of stars, they have the same amount of stars, but we call one a globular cluster because it's not dominated by dark matter, and we call the other one a galaxy because it's dominated by dark matter. And that's the idea that galaxies form in their own dark matter halo, whereas globular cluster doesn't. They form inside somebody else's halo. Now, dwarf galaxies, most dwarf galaxies are dominated by dark matter at most radii. So dwarf galaxies tend to have a lot of dark matter everywhere. A galaxy like the Milky Way does not seem to be dominated by dark matter in the center. And dark matter starts to become more and more important because if you think, so it seems like the distribution as a function of radius of stars tend to be something like this, whereas for dark matter in these galaxies, it perhaps is distributed more like that. So in the center, there are more baryonic matter than dark matter, but in the outskirts, it becomes dominated by dark matter at some point. So it varies from the galaxy to galaxy. And there's a good reason why you should expect to be dominated by baryons in the center, and that's because baryons can lose energy from radiation. So baryons can collapse even further than dark matter. Dark matter cannot lose energy from radiation, whereas baryons can. So if they start the same, then baryons in principle should be more concentrated than dark matter. And so that's why, generally speaking, dark matter doesn't dominate in the center, but it does in the outskirts. Right, okay, so I'm going to save you the drudgery of the full derivations here. But there's an extension to what I talked about yesterday called the Press-Schechter theory. There's something called extended Press-Schechter theory because nobody was more creative, which is an extension of Press-Schechter. And And it allows us to relate the mass function at one redshift to another redshift. So it tells us how mass functions change. And thereby it also tells us how the mass of a halo changes with time. So what people calculated, so Einstein in a few years ago, probably close to 10 years ago now, they calculated that there is a very simple relationship that tells us this omega is a bit like a time variable. This is defined down here. It's about like a time variable. And it tells us that the mass that a halo change, the mass growth of a halo is only related to the variance of the power spectrum. Do you know the power spectrum? You can calculate the sigmas. We did that before the break. At two different halo masses. And you can calculate, this is exactly what I did before the break. That's what I'm not doing it on the whiteboard now. You calculate the variance relative to sigma 8, M8, exactly what we did in the beginning of the morning. You use this expression for this derivative. And then you could just plug these two in here. And you get an estimate for the growth of halo mass with unit time. Okay. And it has a few features. It goes as 1 plus z to the 5 halves. And it goes as the halo mass to 1 plus some small number here, okay, depending on the power spectrum. Okay. So this you can all do. It's just what we did in the morning. It's nothing. There's nothing very magical about it. It's only boring arithmetic. So that gives us an estimate on how dark matter halos grow with time. And that's quite an important number because it basically says, how much new dark matter comes into a halo. And you can do the same thing, do it slightly more carefully. That's done in this paper, but it fits in very, very similarly to the numbers that I showed you. And you can say, okay, I'm actually calculating how much dark matter there is onto a halo. But if I say, on large scales, the amount of baryons that come in is going to be the universal baryon fraction times the amount of dark matter that comes in. Okay, that's what it's going to tell me. So when you do that calculation in detail, you find that the amount of baryons coming into a halo goes as the halo mass to 1.15 and 1 plus z to 2.25. And this is actually, even though I didn't do it all here, you can do all of that completely analytically with there's one number that needs to be calibrated at this Q here. Okay? But all of the rest is analytic. But you can then simulate the same thing. You can calculate a large cosmological simulation, and you find that this is actually in very good agreement. So suddenly you have a simple analytic, this is quite simple, analytic formula that tells you how a halo grows with time. So this is, this is a spherical accretion. But this is crucial because that in principle, this is the amount of fuel that will then come in to the galaxies in the dark matter halo. Okay, it's a fuel theorem. And you need some fuel to run a galaxy. So that's back then to my simple cartoon. And so you have baryons outside falling into this dark matter halo. The rate of that is the function I showed you on the previous slide. But what happens when it comes into the dark matter halo? What's the physics that then happen afterwards? Well, this is usually going to be quite cold. What's inside here is typically going to have the virial temperature of the halo. So what happens when you put a cold clump into a hot gas is that you typically set up a shock. And so what will happen is that you will have your clump with temperature much less than the virial temperature. You have your dark matter halo with Tvir. And as this falls in here, at some point you will expect it to have a shock. And the temperature will go towards the virial temperature. Okay, so that's the idea, is that there will be a shock at close to the virial radius or some place in the dark matter halo. Right there. And that will bring this gas up to the temperature of the halo. Now, whether that happens from an observational point of view is very difficult to say. It's very, very hard to observe this. But we know that it happens in simulation, although it's a bit more complex than my picture here. But let's assume that's what's happening. Then this clump of gas becomes hot. And then it starts cooling down from the cooling function that we had. So if the virial temperature is very high, 10 to the 7, 10 to the 8, then the cooling time is ridiculously long. If the halo is, say, have a virial temperature of 10 to the 5 Kelvin, then the cooling time is really short, at least for solar metallicity gas. And that's when this gas can start falling down quickly and collapse to high density. It will start out here with very low density, but as it cools, it becomes denser, and then it cools even more efficiently, and eventually it collapses and falls into a spherical disk, a flat disk in the center. So it still has the angular momentum, so it will still be rotating, so that it cannot get rid of easily, but it will basically become very flat and very small in the center. So it is possibly useful to see a few examples of what this whole cooling process actually, the accretion process looks like in simulations. And what I'm plotting here, what's plotted here is effectively the accretion rate onto a halo. The units are a bit weird. And in the previous pictures I said it depended on the halo mass to some power 1.115 or so. These are actually calculations from simulations, and they are a bit more complex looking than perhaps we would have liked. But here is a more careful comparison. The comparison here is these colored solid lines are the measurements in the simulation of how much mass is accreted onto a halo of a given mass at different redshifts. Okay? So these are different redshifts, and this is the halo mass. And the dotted lines here is the approximation that I showed you earlier. It's this function. Well, it's this function, but for the halo, not for the baryons. But so you can see that actually is a very good description of simulations. There are some deviations here, but this might be due to the fact that they have finite resolution in the simulation. So it might be due to a resolution problem. At least the authors are not going to say that there is a problem here. Now, what you probably kind of can see in this is that there are also some dotted lines here. And the reason why there are the dotted lines is that there are two ways of accreting gas onto a halo. One is that the halo lives in the intergalactic medium, and as time goes on, stuff will slowly rain onto it in sort of a continuous fashion. But sometimes there might be another halo that comes from somewhere else and collides with it. Okay? And that's a distinct process. It's like it's a real growth or jump in mass. Okay, the theory that calculates these dashed lines assumes there's a smooth accretion. And that's what these solid lines here are too. These dotted lines are these episodic accretion events, like when something collides with a halo. And what you can see is that for each of these, the solid and the dotted line with the same color, there's almost an order of magnitude difference. So it means that those episodic accretion merger events are not important. Okay, they only make up 1/10 of the mass growth of the halos. So we don't need to worry about those very much anyway. So I said this idea of this shock is a little bit more complex than what I said. And the reason has to do with density. So the cooling doesn't only depend on temperature, it also depends on density. So even if your gas is really hot, if the density is high enough, it can still cool very efficiently. So what really happens then? Okay, so in some situations, the drawing there, but I'll draw it again here. Let me draw my dark matter halo again. Okay. Now, assume in this case that I will have things coming in, and at the virial radius, the density is quite low, and the temperature is high. So here, I have inefficient cooling. So that means things fall in. So if as a function of radius and temperature, it starts out at low temperature, then it hits RVir, it jumps up in temperature, and then maybe at some point it will start cooling down. But it jumps up a lot in temperature and stays there. So then basically your dark matter halo has a galaxy in the center, but there's an atmosphere in the dark matter halo of hot gas, which is not cooling very quickly. And that's called hot accretion. So it's hot gas. Gas does not cool down. Typically it should be hotter than 10 to the 5 Kelvin. It's hot gas that's hanging around and slowly rains down on the galaxy. Hot accretion. Now, let's draw the other extreme. Let me draw same halo. But now, I'm going to assume that it's efficient cooling here. And now, what happens? Well, it's still low temperature outside. It might go up a bit, but it cools down again. Okay, because it cools very quickly. It doesn't have a chance to heat up properly, and it cools very quickly. That's the simplistic picture. What's the real picture? In simulations, it's something similar to this happens, but it's not because exactly the reason I'm saying. It's because there is no stable shock. You need a stable shock to get this temperature here. Here it is unstable, and it might break up. And that's cold accretion. And that can then fall in very quickly. It's a very efficient way of feeding galaxies. And this is what this picture that I showed you earlier actually showing us. Here, this becomes hot, and you can see only small pinpricks of cold gas. This is temperature on this side. Small pinpricks of cold gas inside the virial radius. And those are clumps of gas that have been dense enough to shield themselves from the hot surroundings. Okay? So the surface is hot, but the center is not. Okay? It's a shielded, dense enough that it's shielded. But it comes in small clumps, and a lot of the gas is going to be hot. This is slightly lower mass halo, 10 to the 12. This is 10 to the 12.5. Here you see you have these streams that slowly is broken up, but these cold streams of gas that come into the halo. And finally, in the smallest halos, you actually get these streams of cold gas they never get heated up efficiently. They actually stay cold all the way, and they go all the way into the center where they can be turned into stars very efficiently. In this case, it's hard to turn them into stars because they're really hot. A lot of it is quite hot. You need to cool it down a lot. But here it comes in cold, and it's quickly, as soon as it gets dense enough, it cools down quickly. If you put in feedback effects into it, then things look a little bit, oh no, sorry, this is, I didn't put this feedback picture. This is the zoom of the other one, sorry. It's the same thing, but now zoomed in to within the virial radius. And again, you can see these clumps, disrupted streams, and solid streams. And this is a picture that's quite universal. Highest mass halos, accretion tend to be hot, and whatever cold things comes through come in small clumps that are shielded. You go down in mass, you start getting these streams that may or may not be disrupted. Eventually, in the lowest mass, you have cold gas coming all the way into the galaxies. And this is really quite important. And I think perhaps this one and the figure I'll show on the next plot, next slide, are the most important. What this is showing you is the fraction of gas that's been accreted onto galaxies as a function of halo mass at different redshifts that came in hot. Okay, so gas that's been 10 to the 5 Kelvin or hotter. And what you can see is that at low redshift, the green curve, 50% or more of the gas that comes in is actually hot. At very high redshift, the redshift 5, maybe only 20% came in as hot. It actually came in as cold. And that probably means that it was easier to form stars for these high redshift scenarios. But this is the amount of gas that comes into the galaxies. What about the stars? What are stars made of? And that's what they plotted here. So this, what they did in this paper was they asked, okay, let me just look at the stars and look at the gas that ended up in stars. What's the fraction of stars that were formed out of gas that came in hot, like hotter than 10 to the, that at some point in the past was hotter than 100,000 Kelvin? And what they found was that in low mass halos, stars typically formed only of gas that was really cold. The hot gas wasn't important for forming stars. And even in the higher mass halos, 10 to the 12 at low redshift, it never gets above 40%. So this cold accretion, this cold gas that comes in, is really essential for forming stars. Absolutely crucial. But what also is crucial is the star formation feedback and the AGN feedback. Because here's the same halo, but it has one type of stellar feedback, a weaker type of stellar feedback, and an AGN. And what you can see is that when it has a weaker feedback, you have more cold gas in the center. When you have stronger feedback, you have a lot of hot gas bubbles in the center. And so it really is disrupted depending on the AGN activity that goes on. The accretion onto halos, though, because where I pointed at was in the central bit. But if instead you ask what's the accretion rate onto the halo, so at this white circle, well, that actually doesn't depend on feedback. The different line styles here are different models for feedback, and they're not very different. They're different perhaps in the factor of 2, but it matters a little bit, but not very much. The accretion to galaxies, on the other hand, depends quite a lot on the feedback. The two different curves are for different redshift, by the way. The red is low redshift, the black is high redshift. But here you can see there's quite a large difference between different curves. And so the feedback does affect the galaxies, but doesn't affect the halos very much. And that's what you can see here. The effect of this, you can really see it in the center, but outside here, you can see that the appearance is quite similar in all different scenarios. So it's not so important for the halo, but it is very important for the galaxies. Right. So that's more a summary for your reference. What I was going to do now was then to move on to, and I'll probably do that, is to take this and use it to explain star formation in galaxies. So this is one of the things that I wanted to explain this week. So this is what I showed on Tuesday. Okay, this is a plot of the mass in stars, in galaxies, and star formation rate in galaxies in 4 different redshift bins. And we would really like to understand why things evolve in the way they do. So this is a simpler version of that same plot. I just got rid of all the data points and these upper limits, and I just focused on the star-forming galaxies and just using the medians in each bin. So it's a bit simpler. The blue line here is the same in all panels, so you can see how these shift up with redshift. So now I would like to explain that, what's really going on here. And so it really is it's a tight relationship, really, between stellar mass and star formation rate. So how can we use what I just talked about to explain that relationship? Well, before, I think I'm going to remind you again about a couple of things about star formation rates and stellar, which I did talk about on Tuesday, but also mention a bit about stellar masses, just to give you a feeling for how you get this. So to go back, this is a slightly different way of looking at it from what I said on Tuesday. It's a question of looking at physically what's the right way of measuring star formation rate. And the first thing to ask yourself is, what does that even mean? Right? Is it possible to measure a rate? Probably isn't, right? Because that's an infinitesimal time step, so we can't really measure that. The only thing you can hope to do is you can calculate delta mass over delta t, over some delta t. And the smaller that delta t is, the better is your estimate of the instantaneous. Right? So the simpler, perhaps the most direct thing is that you go out, you take an image in the infrared, and you count protostars. Those are stars that are just being formed, and you can count how many there are, add up their mass. You know they last for about 10 to the 5, maybe 10 to the 6 years, and you get an estimate of how many stars are being formed at the moment. That's almost hopeless to use anywhere except in the Milky Way, but it's still interesting. In principle, it's a very good idea. The next one is the Balmer emission line, H alpha. I mentioned that on Tuesday. That's very good because it is only produced by really massive stars. And massive stars live very short. So it's a measure over a delta T of maybe 10 million years. The only problem is that they don't, there could be some lag, there could be some blurring, but typically it's an uncertainty over about 10 million years. So 10 to the 7 years. Then you have the ultraviolet. The ultraviolet is actually significantly produced by stars that are much less massive than those that give you H alpha. So that can give you both O and B stars, and that means that you're measuring your star formation rate over a delta T of 100 million years, 10 to the 8 years. So 10 times longer than you do. And then there are various other ways. Radio, far infrared, supernova remnants. Supernova remnants are hard because they are, of course, the remnants of supernova explosions, but they can be around for some time, and how long they are around depends on the density of the surroundings, etc. But basically, you would like to have something that has a reasonably short time scale. So why do you care about this? Well, perhaps not so much here do you really care, but if you want to compare things, you want to compare star formation rate with gas content. Very often you want to do that because you want to understand what's driving star formation. From an observational point of view, that's hard. Because if you observe a massive star, the gas that formed that star is gone. It went into making that star, right? So you observe some gas and you observe some stars, but they aren't belonging together, right? The gas is here, stars are here, they're unrelated. So sometimes you want to compare those two, you have a problem. But it might be that on large scales, large enough scales, you can actually compare these two. And then it might make sense to do it. What about stellar masses? So this is a slide from Charlie Conroy's annual reviews article, and where he tries to sort of summarize how we get stellar masses. So there are 2 steps to that, 3 steps to it. The first is to make a model. So what's the ingredients of this model? Well, firstly, you have to have an initial mass function that tells you the distribution of masses of stars. Then you need isochrones that tell you the luminosity of a star for its given temperature. And then you need a spectra of stars of different temperatures. So you can combine those things together. You can then produce the spectrum of a stellar population as it changes with time. Single stellar population. You might add in other ingredients like chemical evolution, dust, etc. And finally, you give it a star formation history, and it looks like this. So that's the modeling side. It's basically just taking stars, models of stars, adding atmospheres to them, calculate their colors, and create a spectrum, basically. The second thing is you need to go out and you need to measure, take photometry, or spectra if you can, of galaxies. So here I've measured 4 photometric points. And then the third point is I take this library. I calculate maybe, well, it depends on the person. I usually use a library of about 100,000 of these spectra. And then I take that library and I scale it up in mass until I fit the data. I find the best fit to the data. So you do something like that, okay? And when you found the best fit, you found an estimate of the stellar mass of the galaxy. Because this is one solar mass of stars. And then as time goes on, through the isochrones, some of the stars will explode, etc., so you can account for that. So when you know the best fitting model, you can go backwards here, and you can calculate what's the mass that that model has. So that gives you stellar masses. Okay. Probably going to keep on with this all day, aren't I? Okay, so can we summarize this a bit more simply? Well, Simon Lilly did this in a paper. He took this data and he just says, okay, what's the evolution like? And he found that this evolution in this range from 0 to 1 is well represented by a function 1 plus z to the 3rd power. At higher redshift, he found a shallower slope. It doesn't go as quickly. There's some, yeah. And then you can also take this and divide this by mass, and then you find that the star formation rate per stellar mass goes as stellar mass to the minus 0.1. Okay? So now you have 2 things that you would like to explain. This evolution and that trend. So could this just be because there's a variation in the amount of gas in the galaxies? That's one possibility. But we know there is a large variation in galaxy. But this plot from paper of mine some time ago, I plot the color here indicates how quickly you're going to run out of gas. And most of these galaxies that form a lot of stars, they will run out of gas in 100 million years. Very short time for a galaxy. So you need to have inflow of gas. Otherwise, we're in a very strange time in the universe where all galaxies are running out of gas. That doesn't seem to be likely. So you need to have some sort of infall of gas into it. So let's just make this assumption that the main controller of what's going on is how much gas is falling in and the feedback in the center. So you have gas falling in, but then you have feedback going on, which will try to get rid of gas again, right? So now you can imagine you reach an equilibrium, okay? Infall, outflow, it's in balance. Imagine now that I increase the amount of infall. I got more gas in. What will happen? Well, I got more gas in, so I form more stars, and then that will lead to more feedback, more outflow, and it will stop the infall. So I get out, I have too much coming in, it now got more blown out, and it stops the infall, and then it has to wait until it reaches an acceptable amount again, and then it reestablishes. So it means that you stay in equilibrium. If you push yourself, if you have too little infall, then your star formation rate will drop and your outflow will drop as well. So you always stay in an equilibrium solution. And that's the idea, is that this relationship here, because it's so tight, is an equilibrium solution. That's what's explaining that it's so tight. And the picture that people tend to draw is something like this. You have a galaxy. It's forming stars at the rate m dot star. Some mass is flowing out, some mass is coming in, and into the halo we have this expression we just derived. Okay? So we have an expression for how much comes in through the border of the dark matter halo. Now we need to figure out what's going in here. And if it's in equilibrium, you would expect that the infall rate should give you the star formation rate and the outflow rate. That's the equilibrium solution. So let's do that. Let's assume that we have this equilibrium. That means that the star formation rate is going to be basically controlled by the difference in outflow and inflow. Now, it is quite reasonable to assume that what's going out is caused by star formation, is related to star formation. So let me now look at that. So if I form some stars, some of them will be bigger, some will be smaller. The rate at which I form them is m dot star. It's the star formation rate. It's in units of solar masses per year. Then time goes on. This might explode. The others stay around. This now gives rise to a mass loss due to outflow. It's just a gas being lost by the supernova. This, of course, depends on this, because if this was higher, I got more of these, and I got more of this. And so that leads us to postulate that the outflow rate is proportional to the star formation rate, and we often write it as eta m star dot. And so if I then now go back to my balance equation, which is just a conservation of mass, really. Put that in here. I get m star dot 1 plus eta or that the star formation rate is given by 1 plus eta m inflow dot. So now we have a simple relationship that tells me, given how much, not multiplied by, divided by. So that's a simple relationship if you can tell me what this M infall is. And so what do you take? This is what we had. That's what we started with. This is what comes into the halo. Okay? There's the accretion onto the halo. It's dependent on the halo mass to 1.15 and redshift 1 plus 25. So now I can just do as it says there, I can just make the simple assumption that all the baryons that fall into the halo are going to be turned into stars, or at least some constant fraction. If that's the case, then this is the infall, M infall rate that I need here. And I predict that the star formation rate is going to be of this kind. But I did a couple of assumptions there which are not spelled out. So let me write it down properly. So I'm going to assume that M infall is going to be proportional to dm dt, which is proportional to the halo mass to 1.15 times 1 plus z to 2.25. Okay? That's what I'm assuming. It's my main assumption. Now, what I need is I really would like to have stellar mass, because that's what the measurements, that's what the observations are. So the next thing I'm going to assume 2, that M star, not dot now, the stellar mass is proportional to the halo mass. Okay? That's a more problematic assumption. Well, as you'll see, this is also a problematic assumption, but let's assume so. Then my infall rate is proportional to the stellar mass to 1.15 and 1 plus z 2.25, which then in this case means that the star formation rate over M star is proportional to M star 0.15 1 plus z to 2.25. Okay, so how does that compare to our observational data? Well, the observational data said that the redshift evolution should be 1 plus z to somewhere between 1.7 to 3. So that's not terrible. Okay, that's not hopelessly bad. But the mass dependence should be negative, should be to the minus 0.1. And here I got it to plus 0.1. So instead of decreasing with increasing mass, it increases with increasing mass. So it's the opposite trend. That's not so nice. So what's missing here? What's missing is about heating. At the moment I just said, oh, the baryons just rain into the halo and then they form stars. But I also said earlier that they get heated when they come into the halo. It's completely missing that, and that heating was a big problem. That was what I was saying, right? It's not something that you can trivialize. You can't ignore the fact that it gets heated, because it is a crucial stepping stone. So that, unfortunately, is not very easy to do analytically. Not at all easy. So what I will do is I will take basically a parameterization from a model, and I say that there is a shock effect that heats the gas very significantly, And in this paper, they found that this heating source had this behavior with halo mass and redshift. Okay. Now you can, and so that means that this will modify this assumption. Because this is still the accretion onto halos, but that's not what gets into the galaxy. What gets into the galaxy is this times this psi factor there. And if I put that in, I now get star formation rate of a halo mass, because it's halo mass to the minus 0.1, and redshift 2.63. And that is actually, if the halo mass and stellar mass are proportional, that's actually in very good agreement with the observations. So the zeroth order, what this is telling us is that you get a good description of the observational result if you take just the accretion, the steady cosmological accretion onto halos as the way to feed galaxies, but you take into account that galaxy halos will heat up the gas as it falls in. If you take those two things into account, then basically the fundamental thing is that galaxies are driven and controlled by the grand accretion onto dark matter halos. So it's cosmology that sets the formation of stars in galaxies and not sort of detailed collisions between galaxies. And I think that's everything I put it here. Well, the other thing I also should emphasize again is that also what I needed to do was to make this assumption that galaxies are in equilibrium. And that really is quite a, you know, deep concept in some ways. If I sketch it, right, I am here, I have log mass, log star formation rate, and I have a tight relationship here. If I push the galaxy up in star formation rate, I increase the amount of infall. So m dot in goes up, then the star formation rate goes up, but then the outflow goes up, and that outflowing gas will stop gas from falling in. And it will immediately, as a response, move back down here again, because of m out goes up. So that's why you have this, it really is an equilibrium solution whereas if you try to put more gas in, it will blow more gas out. If you put less gas in, it will wait and then it will blow less gas out, right? And it will keep trying to keep the same star formation rate all the time. Okay, so I have had a couple of movies, so illustration of this whole process. I think we probably can all be ready for that. I'm going to show you two simulations. These are sort of the rulers of the roost today, the state of the art. It's one simulation called the Illustris simulation, led by a group around Lars Hörnquist at Harvard, and the other one is a group led by Joop Shea in Leiden that ran a simulation called the Eagle simulation, which is probably now the best kid on the block. These groups are competitors, and they tend to, you know, be unhappy with each other to some extent, but the fact is that both of them do a really good job now. So let's see, how well can these ingredients, and they basically put in the ingredients we've been talking about today. So this is, yeah. Yeah.
Can you
Uh,
please
uh,
go back to the
here?
the green is the observational data.
Yeah, exactly. So they are basically these data.
But what is the highest redshift that we can?
That I can do some. Okay. So, haha. The two. Well, okay. So to just answer your question directly first, we can do something like this reliably out to redshift of say 4 or 5, something like that. But it's mostly a problem of measuring this quantity here, the stellar mass. This quantity we can probably measure out to redshift of 8. This is star formation rate, so the rate of new stars. That we can measure to really high redshifts, because when you go to very high redshift, you see galaxies in the ultraviolet. And the ultraviolet is directly proportional to the young stars that are being formed. So I can measure star formation rates really well. But I cannot measure stellar masses. So this particular trend I can only trace out to redshift of 4 or 5 for this thing. But there is a complication addition to what you're saying. So that goes down to when you make a plot like this, you always leave something out. Right? Because in this case, I left out all the galaxies that are not forming stars. They are down here somewhere, and I ignored them. The other thing that you what might happen, say for instance, you want to measure these galaxies. So say you wanted to measure this using a line. Okay, so star formation rate is proportional to H alpha luminosity. Okay, let's just assume that. Now let me plot that as a function of mass. Now I'm assuming I'm just at one particular redshift. And so the true values are these ones. But now let me put in a constraint. I need to be able to measure this. And that means that there is an observational limit which is going to be fairly constant, but down here. So that means that when I'm close to this region, I might be biasing my curve upwards. So I might calculate a mean relationship that looks maybe like that, okay? Because I don't see all the galaxies. And at high redshift, this is a big problem. To properly deal with this is a problem. So up to what redshift you can really believe this, I don't really know. Redshift 3 probably, but much beyond that, I don't know. And you can typically only see, some limited part of this relationship. But it is a tricky question to answer properly.
But in the future, we can overcome that observational limit, or is not possible?
I think we can do quite a lot. So with the James Webb Space Telescope, which is going to fly in 2018, we should be able to do a lot better on both axes. And the aim is to be able to calculate this kind of relation out to redshift of 10. That should be possible with James Webb, perhaps. But we hope so. But yeah, you'll have to wait a few more years. Okay, so this is an image created by the illustrious simulation. It's an image of a bit of the sky, just created on the computer. Okay, it looks very realistic. It's very hard. They often, when they give these talks, they show this compared to a real image of the sky, and you have to guess which one is the real and which one is the simulation, and it's very difficult. It's a big thing. It's many hundred megaparsec cubes. It has a mass resolution that goes down to 10 to the 6. and can get down to spatial resolutions of 50 parsec. This is a very large dynamical range. From 100 megaparsec to 48 parsec is a long way. So it's quite an impressive simulation, and it has 18 billion particles. These things are big, right? One output file, one time step is typically of the order of terabytes. So they're big things. Let me skip the image. Let me just go to the movie. So what you're going to see is you're going to see the same as zoom in and then out. Yeah, sorry. No. Oh, Doris Palace. So you see less of it. Don't see it as much because, and that's not so obvious that it should be like that. But it's mostly because if I go back, the smallest particles are 6 million solar masses. Most of these missing dwarfs are much smaller than this. So they simply don't exist in the simulation. In order to see those, you need to simulate, instead of this whole box, you need to simulate one or two of these galaxies. So in this case, it is probably there, but you can't see them because you would need an even bigger simulation to actually resolve them. So yeah, so this cuts off too early to actually see this problem. But if it was a bigger simulation, yes, you would see it. Okay, so what you're going to see is you're going to see a zoom in and a zoom out in different physical quantities. Let me see if I can do it though. Okay, so we start with dark matter. The color is density, and that's a lot better. And we're going to see how this changes with scale. We're just going to move in scale and see how things change here. Here is gas temperature. And you can see there are some regions of cold gas, many regions of quite hot gas. And we're going to zoom in towards this region here, which is relatively hot. But now we're going to see metals. Red here means more metals. Bluish means primordial. And now you see the stars. That's quite a boring picture compared to what you saw before. Right? It's all static. Nothing is changing. We're now going to zoom out again, then you can see better. But it looks quite real. I mean, this is a simulation, right? It's not a real galaxy, but it looks pretty good. Now it's the gas density. So you can see also gas is concentrated. High gas densities are just in small regions. Come on, it's supposed to change to temperature again. Oh, and this is velocity. Okay, so this is actually something I probably should stop a little bit because it's hard to appreciate. So here, what you can see is the gas that's yellow here has large velocities. So those would typically be things that are blown out in explosions, right? Feedback events. So you can see these regions here that are feedback regions, things that have been blown up. And eventually, this moves back to dark matter. And then should you see the credits. So that's really how this thing does. And I think it's hard to get all the impressions, so let's run it again. And just see how, in the beginning, see how it relates the distribution of dark matter and the temperatures. these high temperature regions tend to be dark matter halos. And you can see that, well, it's actually kind of hard to see because I didn't tell you in time. But let me just go back again. Okay, so, oops. So now you can see it's just in the changing. So this is the high temperature region because these are halos of galaxies. And metals are created by stars in galaxies, right? They ejected from stars in galaxies. So in the next bit here, you can see that indeed that's where there is a lot of metals. It's where there are galaxies, right? And this red part, which was the highest metallicity, transitions straight into this. So you can see how metals trace density, trace the centers of where galaxies are formed, because that's where the stars were that exploded and then gave the metals back out. Maybe back to the velocity picture again. It's probably the hardest one to appreciate. And now I'm going to show you the dynamic version of this. And then I'm going to stop because I'm really annoyed at this noise next door. And then I'm going to show you the rest of the other movies tomorrow. So here is the... So now you can see here is the time. It's effectively redshift. Now you're going to spin around. Again, you're going to start out and you're going to see it changing to different phases. And now you have to try to think about the picture you saw before to try to understand what you're actually seeing in this figure. What's being plotted? Oh, come on. You see things really happening here. So does anybody have a feeling for what they're seeing? What's the color? Let me go back again. What's this blue stuff? It's dark matter. So what's then the red and green and yellow? I think it's temperature. It seems to be the most likely, yeah. Actually, I don't have the answer here, but I think it's the temperature. Almost certainly. So at this point, there is star formation happening here. There is gas here, but it's not a lot of it. It's not dominating the output. And that's because the universe is really the peak of star formation activity in the universe. It's about redshift 2. So that's what we're moving to. And that's where we are now. Now when you're starting to see supernovae and AGNs going off and giving feedback to surroundings. And these really are blowing, significant bubbles out. They're really blowing out galaxies if they can. And you can see it happens even in the small ones, but less dramatically. It's really the big ones where there is a dramatic amount of explosions. So now think 100 years ago, people thought the universe was static, but nothing changed. And this is quite different from that. But now, of course, we've gone 10 million years after the Big Bang. Now the universe starts to become a bit boring again. Not so much happening. This is our universe. Right? And now you certainly can see some of the dwarf halos. They're just not as many as there were. But you can certainly see them. They're all these small pinpricks here. Okay. Right. I think we're going to finish. I mean, this is too noisy. I can't hear myself thinking. I'm going to show, I have time for showing these, completing these videos tomorrow, so we can do it then.